Hello, can you please confirm that you can hear me?
Yes, sir.
Okay, thank you. So, let me return to the last topic on which we ended our previous class. Uh, we began magnetism, magnetostatics, and I mentioned to you that magnetostatics, means that things are not changing in time. However, you have to be careful when you consider that point, because after all, you cannot have magnetism of any kind unless you have charges moving. So moving charges implies uh, a current, and so magnetism is the outcome of a current. However, this current is going to be a steady current, and only when a current is steady shall you get a magnetic field that will be unchanging in time. And what do I mean by a steady current? Current is to be understood as the amount of charge that flows past an observation point in unit time. So, at different points of time, when you measure, if you find the same amount of charge flowing past, then you have a steady current. And such a current will give rise to a static magnetic field. A static magnetic field, as in a magnetic field that is not changing in time. Just like fixed electric charges give rise to an steady electric field, a static electric field, electrostatics. And so it is that a steady current will give rise to magnetostatics. Anyway, I touched upon, so we basically, this is the point I made over here. The static charges produce an electric field E and moving charges in addition, meaning the electric field will be there, will also create a magnetic field B. And the observation, just like you have two charges, as in electrostatics, you have two charges. If they are of the same type, they will repel each other. If they are of the opposite type, they will attract each other. So something similar is observed in the case of magnetism as well. It is that if you have two currents, two adjacent wires which are parallel to each other, and if two such currents are taken, you will considered, you will find that the wires will be attracting each other. And if you have two currents flowing in the opposite direction along parallel wires, the wires are parallel, but the currents are traveling in the opposite direction. In that case, you will find that the wires repel each other. So we shall have to now look at this phenomenon in closer detail. And in order to understand that, I also touched upon this point, you will have to understand a little bit of the nature of magnetic fields. So if you have a straight wire carrying a current I in the upward direction, from the bottom to the top, the current goes. In such a situation, you will have the magnetic field going around around the wire in a circular path. And this is best understood by applying the right hand rule. If you take your right hand and point your thumb upwards, then the thumb will trace the direction, follow the direction of the current. So the thumb is like aligned with the straight current path. And if you curl the fingers around your thumb, then the direction of your fingers will trace or follow the field lines that circle around the straight wire. So that is the right hand rule. And we shall use this right hand rule again and again in various cases. So be careful about understand this thing with care. And now we come to an understanding of these two phenomena, namely that parallel currents attract and anti-parallel currents repel. How so? Let us try to see. Just like you have two charges, one a test charge, sorry, a source charge, which gives rise to an electric field, and the other a test charge, which you place in the electric field created by the source charge to test the strength of the electric field. So it is that in magnetism you do something similar. What is it that you do? There's a wire that is carrying a current I. It's a source wire, if you like, a source current. And the source current has given rise to these circular magnetic fields. There are many such circles on a particular plane. And then above that plane, there will be another set of such circles. Below the plane, another set of such circles, like that. So you place another wire in next to the first wire through which a test current is passing, let us say. Now, let us try to understand. Charge particles, let's say positively charged particles. Always remember, current is the flow of positive charges. So basically, although in reality, in a copper wire, what flows are electrons, but you do not consider the flow of negatively charged particles, which electrons are, as the current. Current is defined as the flow of positively charged particles. Therefore, you will have to hypothesize an imaginary a flow of imaginary charge, positive charges in the opposite direction. So if electrons are going in a certain direction, the effect is simulated by a flow of positive charges in the exact opposite direction. And so that is the current. So you have such a current going up. Okay, charge particles in this current, a charge particle in this current will have a value Q. So it's just a whole lot of charges, each having a value Q, capital Q here, flowing up. Remember this is a set of test charges flowing now. So capital Q, as in test charges. Okay, and so what you have is these test charges are flowing with a velocity v in the upward direction. So basically, it has become a test current. Charges flowing with a constant velocity v. Constant velocity, we are talking steady current, remember. So the charges are neither accelerating nor decelerating. If you have an acceleration or you have a deceleration, then you will not have a steady current. You'll have an unsteady current. So the charges are moving with a constant speed, velocity also, if you like, if it's along a straight track. And now let us see what kind of magnetic field do these charges experience as they are flowing through this wire. So the magnetic fields are curling round the first wire. Of course, don't forget that the second wire carrying a current will also give rise to its own magnetic field, but we are not worrying too much about that. Let's say that the current in the second wire is very weak, so we need not worry too much about. So anything that is used to test should just have enough material to feel the field of the source, but at the same time not so much that it will create its own field significantly. So here what happens is that these magnetic field lines are going round and round. Now you apply the right hand rule over here for the first wire. Current is going upward with a value I. You take your right hand, align your thumb sticking upwards along the direction of I, and your fingers are to curl round your thumb. So that is the direction of the magnetic field. So I've drawn the magnetic fields on a two-dimensional plane, but in reality, they are in space. So basically, at this point, they will be coming out. So the field lines are going round and round in anti-clockwise direction, viewed from the top, that is. So from here, the field lines will be coming out, and at this point, the field lines will be going in. So this is the direction of the magnetic field B at this particular point. Field lines are going in. Okay, so B is the magnetic field. So this arrow is drawn with an incline, but in reality, this arrow is going away from you and piercing the plane of the paper onto the other side. Right. So that is how you should see it. Now V is upwards. B is perpendicular to it, but going inwards into the plane of the paper. Now the Lorentz force, which is an experimentally discovered law, Lorentz magnetic force, F mag, is given by this formula Q, which is the charge on, the value of a single charge in the current, because the current is just like the flow of charged grains, really, into V cross B. Now let us look at this V cross B. V is going upwards, B is going inwards. Now, what does the cross product say? That the direction of the cross product, V cross B, will be perpendicular to the plane that contains both V and B. But then there are two perpendiculars to the plane that contains both V and B. So in this case, the plane of V cross B, this is V going upwards, this is B going inwards. So this is the plane, so to speak. And V cross B, now you can apply another right-hand rule, not this right-hand rule, for the right-hand rule for vector cross product. If V points along the direction, take your palm, hold your forefingers straight upwards and your thumb perpendicular to the forefingers. If V is pointing upwards, you sweep if your four fingers, all the index finger, middle finger, ring finger, the little finger, all of them, and if you sweep them towards B, then the direction of the thumb will tell you in what direction the product is going to be, what will be the direction of the product vector, V cross B here. So, fingers pointing upwards, you sweep them downwards towards B, and the sticking out thumb this way will tell you the direction of the product vector. And the product vector times the scalar Q will give you the Lorentz force, V cross B. So you can immediately see if two currents are parallel to each other, because of this magnetic field, there will be an attraction. A very important point. This will only happen if velocity V is non-zero. Otherwise, if you have a zero velocity, if you have a static charge over here, the static charge will not feel any kind of force. And mind you, overall this wire is charge neutral. How so? Because it's made up of both positive and negative charges, except that the same amount, except that it's that with the application of a potential difference across the wire, the free charges, in this case the electrons, have started moving, but the electrons are actually going downwards. But you have equivalently treated the flow of electrons going downwards as a flow of positive charges going upwards. So if you keep a charge over here, just a static charge, it will feel no force of any kind. It is because there is this velocity v that you feel this Lorentz force. As a charge, a charge will feel the Lorentz force. Excuse me. So that is what it is. So that explains parallel currents attract. What about anti-parallel currents? Same thing. If you go down this way, then immediately V will change direction downward. But B continues. B is due to the first current. B continues to go into the plane of the paper in the same direction, except that V goes downwards. So now when you have V going downwards, immediately there will be a negative sign over here, meaning the force which was earlier going inwards will now go outwards. So that also explains why anti-parallel currents repel each other. So you can see that this is not really a static business. It is happening because of two things. This Lorentz force is happening because of two things. It is not really electrical in nature. It is something different. And what is that something different? The something different is magnetic field due to the first wire. So this force would not have existed if you did not have two things. First, magnetic field due to the first wire, and second, motion of charges in the second wire. If V were to be zero, there would have been no force. And also, don't forget something, if the first wire did not have a current flowing through it, then B would have been also zero. So this is a new kind of phenomenon we are looking at, whereby moving charges is giving rise to an effect. We call that effect magnetism. But magnetism was historically understood to be due to things like North Poles and South Poles. Well, no, not really. It is due to the motion of charges. We shall look at this point in greater detail later, but for the time being, I'm just reminding you of that one point which we discussed in the early stages of our course, that magnetism must not be understood to be due to the existence of material or things like material elements like a North Pole or a South Pole, but due to charges in motion. Okay. So now let us see what happens. A test charge Q in motion can in general feel two different kinds of forces. What are they? There could be, we have just drawn magnetic field over here, but there could be electric field also. There could be some source charges somewhere unbalanced, which will give rise to electric field also. So if you place a test charge in both an electric field due to static charges, let us say, or charges in motion, that doesn't matter. Electric field due to charges and magnetic field due to a current, then the total force experienced by the test charge capital Q will be given by this. F will be equal to capital Q into E, which is the electrostatic part of the total force that it experiences. And then Q into V cross B. This is the Lorentz force that the test charge experiences. So in many cases hereafter, we shall have to refer to this kind of a feature, that when a test charge is placed in both an electric and a magnetic field or electromagnetic field, then they will experience a total force, which is given by this. This is the electric component and this is the magnetic component. Okay, magnetic force, there's something very important, of course, also over here. This part, and magnetism, this part, can only be experienced by something that has charge, Q. Something that is charge neutral overall will not experience neither. So you need, just like to experience gravity, you have to have a non-zero inertial mass. Similarly, to experience electromagnetism, an object has to have a non-zero test charge, non-zero value of its test charge. Okay, then there's the next point. Magnetic forces do no work. Okay, let us try to see what is the usual definition of work. Work is defined as force times displacement. Okay, I mean force dot displacement, it's a dot product. And so if, by the way, work, I mean displacement and force are perpendicular to each other, then there will be no work. Okay, that much is to be understood. Now, what is dl? dl is written as v dt. Remember, v is dl dt, displacement per time, dl dt. That is v. So dl, the displacement, is velocity into the time taken. So v dt. So if your force is a magnetic force, then you write it as q into v cross b dot v dt. Dot dl, I'm substituting with v dt. And that will be equal to 0. Simple thing to understand. Why should it be equal to 0? Look at with this product v cross b. Whatever you get V cross B, it must be perpendicular to the plane that contains both V and B. That is the definition of a cross product. A cross product gives an outcome, has an outcome that is a vector perpendicular to the plane that contains the two initial vectors. V and B are contained on a plane, so the outcome of this cross product will be perpendicular to this plane. So that will be perpendicular to V. If this product is perpendicular to the plane that contains both V and B, then it must also be perpendicular to V, of course. So if you have two perpendicular vectors whose dot product is taken, then the dot product will be 0, because the definition of a dot product is the magnitude of the first vector times the magnitude of the second vector. This is the first vector. V cross B gives the first vector, which is a product, and the second vector is V. So magnitude of the first vector times the magnitude of the second vector. When you take the two of them, um, into cos of the angle between the two of them, and the angle between the two of them is 90 degrees. So cos of 90 degree will be 0. So that is the answer. So basically what happens then, magnetic forces alter the direction in which a charged particle moves, but they cannot change the speed. Why not? Let us try to see. See, on the application of a force, velocity will change. That is to be understood from Newton's first law. What does Newton's first law of mechanics? Let us go back to that once again. The first law of mechanics says that every object tends to maintain its state of rest or uniform motion along a straight line. Meaning, state of rest means uniform motion means constant speed. Along a straight line means constant direction. So when you say every object tends to maintain its state of rest or uniform motion along a straight line, that is to say, or constant velocity. Every object tends to maintain its state of rest or constant velocity unless an external force acts on it. Somebody is asking, can we say it using divergence and curl? Probably, I wouldn't know, but I'll think about it. Somebody's asked this question, but I'll think about it. I can't say offhand. Let's see. So maybe we can take up this point at the end of the class. I should try to understand the context of the question better. So anyway, so if you apply a force, the velocity state will change. That is from Newton's first law. Otherwise, if you do not apply a force, the object will be in a state of rest. That is to say, zero velocity or constant velocity, constant non-zero velocity, which is uniform motion along a straight line. So if you apply a force, the velocity of an object will change. But then this is a force on the application of which no work is being done on the object. That is an interesting point. Why not? So suppose you just imagine you have a car, you pushed it from behind. So by the action of your pushing, which is to say you have applied some force, the car was stationary earlier, you have applied some force on it, and with the application of the force, the car undergoes a little displacement. Okay, so basically the car has moved. Earlier the car was static, but now on the application of your force, the car has moved, which means the car must have gained energy. Earlier it was stationary, but then when you have pushed it, it has started moving. So it has gained kinetic energy. Otherwise it would not have moved. Kinetic energy is the energy that is attributed to motion. So where has the car got this extra kinetic energy all of a sudden? Well, from the work that you have done. Work is a form of energy. Energy is a conserved quantity. Do not lose sight of that fact. So the work that you have done in pushing the car has gone into the car as its energy, kinetic energy, and the car has moved a little forward. Okay, fine. But if you follow this point carefully now, here you are applying a force, which means velocity will change. But the force is not doing any work, which means no energy is going into the particle. If no energy is going into the particle, its kinetic energy is not changing. And what is kinetic energy? Half mv squared. So basically, it continues to have the old kinetic energy as it had earlier, half mv squared, whatever. So what is v squared? V squared is vector v dot vector v, dot product of the velocity vector with itself. The outcome is a scalar. So half mv square is a scalar quantity. So if it is a scalar quantity and it is not changing, mass of course is constant property of the object. So if the energy is a kinetic energy is a scalar quantity and it is not changing, then you have to conclude that the scalar value of the velocity is not changing, which means that here is a situation whereby you have applied a force, the force has changed the velocity, but the force doesn't do any work, force does no work, and as such the speed, as such the kinetic energy is unchanged, and therefore its speed is unchanged. So here's a force, the application of which has caused a change of the velocity, but not a change in the speed, which means it has only changed the direction. Velocity is both magnitude and direction. It will not change the magnitude or the speed of it, and that is what it is. Magnetic forces alter the direction in which a charged particle moves, but they cannot change the speed. A standard example of such motion is circular motion. In circular motion, a particle is always a steady circular motion, let us say. A particle is always changing its direction, which is tangential along the circular path. Therefore, its velocity is always changing. However, its speed is not changing. Therefore, it just continues to travel along the circular path at a steady rate. So that is what it is. Magnetic forces do no work. Okay, let us now look a little. So all of this thing, since we are talking about particles moving, charged particles moving in a circular, I mean, under the effect of magnetic force or whatever, experiencing a magnetic force, moving charged particles are currents. So we shall now look at currents in more detail. What are they? Certain properties of currents. Okay, first, currents arise due to moving charges. Standard thing to understand, not a very difficult thing. Amount of charge flowing past a point in unit time. That is how a current is defined, which is a vector. Now, let us see. It's a vector. Now, here I have written some formulae. You have a wire that contains uh, lambda amount of charge per unit length, right? So that is the line charge density. Lambda is the line charge density. I have supplied you with the book of David Griffiths. This discussion is held in much greater detail in section 5.1.3, 5.1.3 as I've written over here. So you can look it up for greater understanding, more clearer understanding. Lambda is the line charge density. So in a small segment of the wire having a length delta L, the amount of current that will flow past in a time window of delta T will be lambda delta L. So lambda delta L divided by delta T. And delta L by delta T, going in the limit, will give you lambda into the velocity, V. So lambda into V, velocity V is I, the current unit. So it's the current, the vector that you have. So that's a basic property. Now I've mentioned another point over here. Flow of positive charges in one direction is equivalent of the flow of negative charges in the other direction. So that is another point you should consider. Here you can see for yourselves, the Lorentz force is defined as Q into V cross B. It will not at all incidentally change the Lorentz force behavior. So let's say positive charge is going in a certain direction with a velocity V. If I treat that as the flow of negative charges in the other direction, then Q will go to minus Q and V will go to minus V. But the two minuses will cancel each other and you'll continue to have a plus. So Q into V cross V will continue to be this. So that is the other feature. So flow of charges, and the unit of current is 1 ampere. 1 ampere is in the SI system is defined as 1 coulomb of current per second, traveling 1 coulomb of 1 coulomb, sorry, 1 coulomb of charge, 1 coulomb of charge traveling past the observation post in 1 second time, in 1 second of time. So that is defined as 1 ampere. That is the SI unit of current. Okay, now let us go to infinitesimals a little. Here we are. V is defined, understood to be dl dt, magnetic force. So instead of having a full charge Q, if you have a small charge element dq, differential, then the total magnetic force will be integral of dq V cross B. Okay, I mean, there's a greater detail of this calculation over here. I don't want you to worry about this point too much. Here we have it in a much simpler fashion, dq into V cross B. You write V as dl dt, as you have over here. And then this dt you shift below dq. dq dt will be your current, I dl. So basically, when you want to write this Lorentz force formula for an infinitesimally small amount of charge flowing through in time, infinitesimally small amount of time dt, and would like to write it in terms of the current I, this instead of q, you want to write this thing in terms of the current I, then this is the formula, I into dl cross b, and then you have the integral over there. So anyway, so a little bit of mathematical discussion as we have done over here. Now our task will be to just round up this whole idea. So we have discussed the idea of static charges in all our discussion of electrostatics, and they give rise to the electric field, capital E, vector E. And then we have discussed steady currents as we are doing right now, and that gives rise to magnetostatics with the magnetic field B. So we have already seen one experimental law. Remember, we are not doing mathematics. Our first principles are to be seen from nature, and the first principles of nature are always physical. We are doing physics over here. In electrostatics, you started with two fundamental observations taken from nature, namely the Coulomb electrostatic force, and second, the principle of superposition. So here also, one observational fact that we have seen is the Lorentz force. And then the second thing that we are about to begin is another experimentally observed law pertaining to magnetism. And you are familiar with it from your school studies. It is the Biot-Savart law. So let us now look at it in closer detail. What is this whole business about? Uh, Follow carefully the diagram first. You have a current. Ideally, I mean, current is a flow of charges along a wire. I mean, you can either have an infinitely long wire, you can't have a current in a finite line segment. You either have an infinitely long wire, or you can close the wire upon itself and form a closed loop so that there is no beginning point or ending point, and the current keeps going round and round that wire forever. So that is the sort of situation we have. We have got a closed loop, but it could have been an open wire also, but then that open wire has to be an infinitely long wire. Okay, so here's the current going round and round this wire. You have taken a small line segment on this wire called DL. Now, due to the current in this wire through this small line segment, what should be the magnetic field at a point P here, which is a displacement R away from the line segment DL. Okay, so this small line segment is to be treated as an infinitesimally small object, but not exactly of zero dimension. It still will be linear, therefore it will have a small one-dimensional linear value dl. So this is an experimental law. Okay, now the magnetic field over here due to this small line segment dl will be dB. dB will be equal to mu naught by 4 pi r squared into I dl into dl cross r cap. Let us now try to understand this formula. It's just a mathematically expressed form of the Biot-Savart law, which is an experimental law. Let us try to understand the similarity of this equation and the similarities and the differences of this equation with respect to the Coulomb force in electrostatics. Let us try to see. In Coulomb, you have electric field due to a point charge. And here you are looking at a magnetic field due to a small line segment containing a current. Remember, electric field due to a point charge. A point charge is a zero-dimensional object, whereas this is a small one-dimensional object, so line segment. And so what is the magnetic field due to this small line segment? In Coulomb, if you have a static point charge Q, then the electric field due to that point charge will be Q divided by 4 pi epsilon naught r squared r cap. That is how you write it. Okay, so here in the denominator, you have a 4 pi as in Coulomb. In the denominator, you also have an r squared as in Coulomb. But in the case of Coulomb, you have epsilon naught in the denominator. Here you don't have epsilon naught. Here you have got mu naught in the numerator, not in the denominator. In the numerator, you've got mu naught, which you can actually see as 1 upon mu naught in the denominator. Either you write mu naught up here, or you write 1 upon mu naught down there. Hereafter, you will see this thing happening again and again. This is a forewarning in the sense that electricity and magnetism are two faces of the same coin, namely electromagnetism. And this, wherever you see an epsilon naught in the electric field, in the equivalent or the cognate magnetic formula, you will have to substitute the epsilon naught with 1 upon mu naught. This is the first such example, as you can see. In Coulomb, you would have had 4 pi epsilon naught r squared in the denominator. In magnetism, as in Biot-Savart law, you will have 4 pi 1 upon mu naught r squared in the denominator, and then that 1 upon mu naught will go up there as mu naught in the numerator. Okay. The I here is the equivalent of Q in Coulomb. So you have Q by 4 pi epsilon naught r squared. Here you have got I by 4 pi 1 upon mu naught r squared. So those are the kind of similarities and differences. Now let us come to the last part, the unit vector. In Coulomb, you have the unit vector r cap. Here you don't have just the unit vector r cap. What is r cap? Let's see. This is vector r here. That is equal to magnitude r multiplied by the unit vector r cap, as you can see here. So that is what happens in electrostatics. The electric field has got the direction of the radial vector given by r cap. Here you don't just have an r cap, you also have a dl cross going along with it, dl cross r cap. So what is the direction? That will be determined by your, or known by your knowledge of the direction of the cross product of two vectors. For instance, here you have got dl, here you have got r cap in this direction. So it will be dl cross r cap. R cap has got the value of, unit value of 1. It's a unit vector. So magnitude of dl into 1, which is the magnitude of the unit vector r cap, into times the direction of the perpendicular to the plane that contains both dl and r cap. So that is where we shall soon see where an example where we will apply this idea. So it is an experimental law. Um, Mu naught is the permeability of free space, as epsilon naught was known to be permittivity of free space. And here's the magnetic field. Where you integrate this thing, integration of dB will give you B. Mu naught I, we are talking about a steady current still, so I is not a variable. In any case, the integration is not over time. So mu naught I by 4 pi, you have taken it out. And then you have got dl cross r cap divided by r squared. And then you integrate this thing. The unit of magnetic field, SI unit of magnetic field, is Tesla. Here, otherwise, you can see it also as Newton per ampere per meter. Where's this thing, Newton per ampere per meter, coming from? Well, it's there. You can see that thing. Force is equal to I into dl into B. Force has got the unit of Newton. I has got the unit of ampere. We are talking SI units, of course, MKS system. Newton, ampere, meter. So B, magnetic field, will be Newton per ampere per meter. Don't get into too much complication about all that. Just write Tesla. That's the definition. That's the unit of magnetic field. So the unit of the electric field is volt per meter. And the unit of the magnetic field is Tesla. Okay. Now we shall apply the Biot-Savart law to an example. And I've also, there's something I've mentioned over. The integration is along the length of the wire. You see, DL is this line segment on the wire. So basically, DL with an integral meaning, with something else going on besides, r cap by r squared, that is there. But DL with an integral meaning that you have to gather the value of cross r cap by r squared all around over the length of this wire. So DL integrated. So the integration is along the length of the wire. We shall now apply this Biot-Savart law to an example. Magnetic field of a long straight wire, as written over here. I have written the Biot-Savart law for a closed loop. See, current has to pass all the time. So you either have an infinitely long wire, which is just a hypothetical scenario. You can't have an infinitely long wire in a practical sense. Or you can make the current go round and round in a closed loop and sustain it forever. So there you are. I have taken an infinitely long wire. This line over here with a double arrow here, with a double arrow here, is my infinitely long wire. Current I is passing through this wire, and I am using the S phi Z coordinate system, as you will soon realize, except that the Z axis, instead of pointing upwards, has been made to fall down on the ground. You imagine the Z axis to be X along one axis, Y along one axis on a horizontal plane, and perpendicular to the plane going upwards is the Z axis. Well, I've just, like in a cylinder. But I've just rolled the cylinder over onto its side. So this is the radius S of the cylinder. The cylinder is lying on the side. Okay. Just a minute. Now, we'll apply the Biot-Savart law over here. This is the point P. This is the line segment DL. Here, we have chosen this small line segment DL, which is DZ. This is Z. This is the Z axis. Right. This is the Z direction. A small line segment on the Z axis, DL will just be equal to DZ. DZ is DZ cross DZ Z cap. That is what it is. This is the observation point P. You are interested in finding the magnetic field at this point P. Okay. Here, as in this thing. This P is a displacement, radial displacement vector R away from DL, the line segment DL. And so it is that this P is a radial displacement vector R away from this small line segment dz. Okay. Now there are two distances. This is the long, infinitely long current carrying wire. P from this point dz, which is infinitesimally small, I shouldn't use the word pz, point, I should say small line segment, infinitesimally small line segment dz, the distance is vector r, or displacement is vector r. But then P has also got a shortest path distance from this wire, it is S. So from here, from the wire, the shortest distance to P is S. And S is perpendicular, shortest meaning perpendicular. Otherwise, your actual source line element is here. And this is the test point, P. That is a displacement, radial displacement R away. But this is the shortest distance, this is S. Okay, S is fixed because point P is fixed. Point P is fixed with respect to the wire, therefore S is fixed. But this dz, it can move up and down. It's just like a small slider on a long wire that you are riding. So this can go to the right, this can go to the left, whatever it is. So if it goes to the right or left, then accordingly the value of Z will change. If Z changes, R will also change. Right, if this thing goes this way, R will also change. And if R changes, then theta will also change. So there are three variable quantities in this geometrical representation: theta, Z, and R. This is 90 degrees, this is 90 degrees, this is the z-axis, this is the S vector, this is like a cylinder whose axis is along the z-axis, and the cylinder is now lying on its side, on the roll curved barrel face. I is going along the z-axis. Okay, now we shall apply the Biot-Savart law over here at the point P. What is it? Mu naught I by 4 pi r squared dl cross r cap. Let us see now. Mu naught I by 4 pi r squared. Okay, fine. We are now just looking at the magnitude part of it, but the vector part will also be very important. Now, you have got dl cross r cap. What is dl? dl is dz. R cap is this unit vector along this radial direction, along this displacement, the hypotenuse. Okay. dl cross r cap, or dz cross r cap in this case, how will you find it? Definition is magnitude of the first vector, which is dz or dl. dl in this case dz specifically. So that is magnitude dz times magnitude of the second vector, which is the unit vector r cap. So magnitude of r cap will be 1, nothing to write, times the angle, sine of the angle between the two. dz is going in this direction from left to right. R cap is going along this hypotenuse. So this whole angle is trapped between the two vectors. dz is going along the direction of the double arrows. And r cap is going along this hypotenuse given by the single arrow. So these are two vectors, one going from left to right and the other going along this incline. What is the angle between the two? 90 degrees plus theta. So definition of cross product is magnitude of the first vector, dz in this case, magnitude of the second vector. Second vector is r cap, unit vector. So 1 in this case, times sine of the angle between the two. Sine of 90 degrees, it's theta cap. 90 degrees plus theta, I'm sorry. Okay, for the time being, we're just looking at the magnitude. We'll come back to the direction also. I have not written any vector over here. That is the magnitude of the field over there at this particular point. Okay, now we shall have to see there are three variables in this formula: dz, r, and theta. Theta here, z here, r here. As you keep moving this small line element up and down this wire, all the three quantities will change, three variables will change their values. So you will now gradually reduce them in number. Let us first see. Z by S, perpendicular by base, is equal to tan theta. Z by S is tan theta. Therefore, dz will be equal to, remember, S is fixed because P is fixed. P is the shortest distance from the line. S is the shortest distance from the line to the point P. S point P is fixed and nobody is also moving this wire. So this distance is the shortest distance between P and this wire is a fixed quantity. So that's a constant. So dz will be S d tan theta. And what is d tan theta? Sec squared theta d theta. So first we have eliminated z over here. dB is equal to mu naught by 4 pi by r squared. dz we are writing as s sec squared theta, s sec squared theta and d theta. What about sine 90 degrees plus theta? That by trigonometric identity, sine 90 degrees plus theta is cos theta. We are writing as cos theta. So it is s sec squared theta cos theta d theta by r squared. Okay. Now we shall also have to eliminate the variable r. So we had three variables over here, z, theta, and r. Now we have got only r and theta in this formula. Now we will eliminate r from this. So let us go back to our diagram. Base is s, hypotenuse is r. Base upon hypotenuse is cos theta. So s by r is equal to cos theta. S is equal to, therefore, r cos theta. Therefore, the variable r will be equal to s by cos theta, which is s sec theta. Makes our task very simple now. R squared will be written as s squared sec squared theta in the denominator. After that, sec squared theta and sec squared theta will cancel. S here and s squared down here will also cancel, and you'll just have 1 upon s, mu naught I by 4 pi, 1 upon s, cos theta d theta. B will be directed along phi cap. I'll come to that point shortly. For the time being, let's just worry about this part. Cos theta. So I can now integrate between two arbitrary limits, theta 1 and theta 2. Integral will give us b here on the left hand side, and on the right hand side I'll get mu naught I by 4 pi s, and then this will go from theta 1 to theta 2, two arbitrary limits. So sine theta 2, so integral of cos theta will be sine theta. So sine theta 2 minus sine theta 1, mu naught I by 4 pi s, sine theta 2 minus sine theta 1. Now we are talking about an infinite wire. So what are the boundaries of an infinite wire? Let us go back to this diagram. The wire will go this way to infinity and this way to infinity as well. And if this point goes, this small line element goes to infinity, then this theta will keep increasing. When this thing goes to infinity, the hypotenuse and this thing will become two parallel lines. And this angle will become 90 degrees on the positive side. Starting from here, going all this way, this angle will become 90 degrees. And starting from here, likewise, going all the way to the negative end, this angle will become 90 degrees. So basically, if you want to integrate for the effect coming from this wire in full, coming from minus infinity and going to plus infinity, correspondingly, this will become plus 90 degrees. This angle theta will become plus 90 degrees on this side and minus 90 degrees on this side. In that case, the lower limit will be minus pi by 2 and the upper limit will be pi by 2 in an infinite wire. And so sine pi by 2 will be equal to 1. Sine of minus pi by 2 will be equal to minus 1. So B will be equal to mu naught into I by 4 pi s into 1 minus of minus 1. And that thing will be equal to plus 2 here and 4 pi here will cancel. So you will have mu naught 2I by 4 pi s. Now phi cap. Where have I got this phi cap from? Let us go back to the diagram. B will be directed along phi cap. I have written over here. Let's go back to the diagram. This is a cylinder. The cylinder is lying on its side. You are aware of cylindrical coordinates. Z is the axis of the cylinder. S is the radius of the cylinder from the Z axis, and phi is the angle going round and round, pointed tangentially to the curved barrel face of the cylinder. Let us now apply the rule of cross product dl cross r cap. So this is dl, dz going from the left to the right. This is r cap going from here to point P. Both dl, dz and r cap are lying on the plane of the paper. They're lying on this white plane, right? What is the direction of a cross product of two vectors? That direction will be perpendicular to the plane containing the two vectors. And this paper is the plane that contains the two vectors. One vector is the infinitesimally small line element dz, and the other vector is r cap. So it is either coming at this point. You have to find the vector at this point. The vector is to be found at this point, the direction. So at this point P, the vector could either be going right towards you, coming out of the plane of the paper, or going into the plane of the paper, because there are always two perpendiculars to a thin sheet plane. So which perpendicular are you talking about? Well, that depends on the order in which you have put these two quantities, first vector and second vector. Sweep the first vector by your fingers towards the second vector, and the direction of the thumb will be pointing towards you. You can see that. So at this point, the magnetic field vector is pointing right towards your eye, if you're looking at this point right at this moment. So it is coming out of the plane of the paper, it's pointing towards your eye. And then just imagine you have gone down to this side. Down to this side, our cap will be just the mirror image of this diagram above this horizontal line. Our cap will be down this way. Okay, so dz is the first vector, r cap will be down this way, hypotenuse is down this way, dz cross r cap. At this point P will have a mirror image point down here somewhere, meaning it will be drilling into the plane of the paper. So at this point it is coming out, below somewhere here it is going in. So basically the magnetic field line is circling this wire round and round like that. As the current is going in this direction, you can immediately apply the right-hand rule for finding magnetic field. I is going in this direction. If that is the direction of your thumb, hold your palm of your right hand flat. The direction of your thumb will be horizontal, going to the right, from the left to the right, and the direction of the curling fingers will come out at this point and go into the paper. So that is the direction of the magnetic field. So the magnitude depends on S, as has been written in this formula. The magnitude, now you see that B is equal to mu naught into I by 2 pi S phi cap. Mu naught is of course a universal constant, so is 2 pi. I for a steady current is a constant quantity. So what are the variables you have? You have only S as a variable, the radius of the cylinder, and phi cap. If you go back to this diagram, which I showed you, here we are, or maybe even this one. I is along the z-axis, S is the radius of this circle, and depending on S, the magnetic field, as you can see, depending on S, the magnetic field will be mu naught I by 2 pi S. So strength of the magnetic field, mu naught is a constant, 2 pi is a constant, I in a steady current is constant. So mu naught I by 2 pi is a constant package. So B is inversely proportional to S. S is this radius. If that is the radius S, Then as we go to outer and outer radii, S becomes large, the magnetic field becomes weaker and weaker. So B is inversely proportional to S. And the direction of B is along the direction of this circular path, whose unit vector is phi cap. So this is phi cap unit vector. That is what you have. Okay, so let us now look at this statement. Direction of B is along phi cap. As I have mentioned over here, B will be directed along phi cap. I hope you have understood this point. So magnitude changes along S, direction changes along phi cap. This is very different from electrostatic field, Coulomb electric field. What if I give you a source charge Q? Here you have a source current I. Remember, current gives rise to magnetic field, and charge gives rise to an electric field. So I give you a source charge Q. What is the strength of the electric field? Q divided by 4 pi epsilon naught R squared R cap. Meaning the magnitude and the direction both depend on R. Magnitude goes, electric field goes as 1 upon R squared. This is proportional to 1 upon R squared, inversely proportional, inverse square formula. So goes as 1 upon R squared. But the direction continues to be along the R vector, R cap, Q divided by 4 pi epsilon naught R squared, R cap. But here, in this case, the magnitude is dependent on the S coordinate, but the direction is along the phi direction, unit vector phi. That is an important feature of the magnetic field. So they just keep rolling round and round the current, and it has got non-zero divergence. Somebody a while ago was asking for a non-zero, I mean, in terms of divergence and curl. I'll take up that question at the end of the class. We have about 14 minutes left to the end of the class. After that, I'll take it up. So the current goes, I mean, the vector field, the magnetic vector field has got zero divergence, but a lot of curl, meaning curling round and round, going round and round. That is the idea that you have. Okay, so now let us take the divergence of this magnetic field. I told you that the magnetic field will have zero divergence. That you should immediately be able to figure out from the diagram itself that I've just shown. But can we apply this formula to a magnetic field and check for ourselves whether it shows zero divergence or not? In cylindrical coordinates, given a vector A, the divergence of the vector is given as 1 upon S del del S of S into A subscript S. A subscript S is the S component of A into 1 upon S del A phi plus del del Z of AZ. Okay. If you look at the magnetic field, it has got only unit vector phi cap, meaning there is nothing like something into S cap plus this thing into phi cap plus this thing into Z cap, something else into Z cap. It has got only a phi component. Therefore, B S, A subscript S, like that you should have a B subscript S, but that thing is zero. So B is zero S cap plus phi component that you have, and then zero Z cap. So that is how you should see it. Therefore, for the divergence, this part will anyway be zero because the S component is, this thing is zero. This thing will also be zero. So you'll just be left with 1 upon S del del phi of A phi. And what is, A phi is the magnitude part of B. I've written it in terms of a general vector A. So that is mu naught I by 2 pi S. So mu naught I by 2 pi S I have written. Now, there is no phi inside here, so del del phi of this quantity will be zero. The only variable is S. It does not depend on phi. The magnitude does not depend on phi, the direction is dependent on phi. So del phi of this quantity will be 0, so 1 upon s into will be equal to 0. So divergence of B is equal to 0. So this is also one of the 4 Maxwell equations. I haven't exactly gone through a formal proof of it. I have just discussed it with the help of an example that we have just got in front of us, namely the magnetic field at any point due to an infinitely long current carrying wire. And what is the strength of that magnetic field? The strength of the magnetic field will be mu naught I. Mu naught is a constant. I is this current by 2 pi into S. 2 pi by 2 pi S. What is S? S is the shortest distance of your measuring point from the wire itself, which is the perpendicular distance. That is what it is. Okay, so this is one of the Maxwell equations that you have got. So earlier we had looked at divergence of E. Divergence of E is equal to rho by epsilon naught, which is Gauss's law of electrostatics in the differential form. And now you have got divergence of B is equal to 0. So one of the 4 Maxwell equations. We shall just apply this idea to an example using the Gauss divergence theorem on a magnetic field. Divergence of B d tau, volume integral, closed surface flux, B dA. Okay. We are going back to the old idea of a magnet having a north pole and a south pole. So out of this north pole, the magnetic field lines are coming. So these are the magnetic field lines. You draw a surface, a Gaussian surface, an imaginary Gaussian surface here, and then you will see that since divergence is equal to 0, divergence of B is equal to 0, then the closed surface, magnetic flux over a closed surface vanishes. Closed surface integral will also be equal to 0. If that is so, how do you reconcile this understanding with the geometry of the system? It is happening because of divergence of B is equal to 0. I've discussed this thing in the case of solenoidal and irrotational fields earlier. Long ago, I discussed these things in that case. Divergence of magnetic field is equal to 0. It implies making closed loop. No, I shouldn't say closed loop. Closed loop comes from Stokes's curl theorem. Curl of a vector goes to the line. Curl of a vector integrated over an area. Just look at Stokes's curl theorem. Curl of a vector integrated over an area goes to a line integral. Sorry, integrated over a surface goes to a line integral. But here, there is no loop. Volume integral is collapsing on a surface integral. Loop implies integral dl, line element, integrate over a line. This is a closed surface integral. But let us look at this closed surface integral. What do I mean by magnetic flux over a closed surface vanishes? Magnetic flux over a closed surface vanishes means just look at this smaller Gaussian surface, dotted surface. A field line is going out, and again it is going in. It is coming out here, again it is going in. So the number of time a field line goes out is also equal to the number of time the field line goes in. Look at the larger field line. It is coming out over here, and then here it is going in. At this point, it is going in. It is coming out here, and at this point, it is going in. So that is the condition that you have. So net flux, the number of times a field line crosses this closed surface, will be equal to 0. Whatever number of positive going out is equal to the number of times the negative going in. So that is what you have. Okay. So magnetic flux over a closed surface vanishes. So divergence of V is equal to 0. By the way, I'll just give you a simple example of this thing. Maybe you've heard of something called sunspots. You see, the sun is made up of hot plasma. The sun is so hot that in an atom, the electrons and the sun is mostly made up of hydrogen. So it's proton and electron. Let us just look at hydrogen only. So it's so hot that the atomic structure also disintegrates. When you heat something, the structure disintegrates. For instance, structure of ice will disintegrate to give you water. So something like that. So under extreme conditions of temperature like 20 million Kelvin inside the sun, the atoms also disintegrate. Protons and neutrons become separated. Okay, sorry, protons and electrons become separated in the hydrogen atom. So the sun is a hot plasma now, and charged particles are moving around. So if they are moving around, they will give rise to an electric field. Imagine this thing to be the surface of the sun, this Gaussian surface. Imagine that to be the surface of the sun. Sometimes what will happen is that the magnetic field lines will pierce the surface of the sun. But then again, they will close in. So the point where they pierce the surface of the sun will be a little darker. They are a little cooler than the rest of the solar surface. And so those are the sunspots. So that those through those points the magnetic field lines come out, but again they go in, and the hot solar material will actually pass through this tube and go back again. Had it not been for this formula, divergence of B is equal to 0, had it not been for this formula, these field lines would have had an open path, like this is a zero divergent field line. So it will not have an open path. Had it been something like the field lines of a point charge, then they would have had an open path, and imagine all that hot material would have come out of that open path and destroying everything, frying everything as it would have gone out, all the planets and everything. So this whole formula, this divergence of E is equal to 0, is of great importance. The magnetic field lines are zero divergent field lines. They will always close upon themselves, and any hot plasma material will be confined within the these magnetic tubes. Incidentally, the Russians were the first to design a technology known as tokamak technology. Here in Gandhinagar, there is the Institute for Plasma Research. They have also got a tokamak. So a tokamak is something, it's a magnetic bottle. Like you want to confine some fluid material. Let's say just simple for the sake of simplicity, you keep water in a bottle or a glass, right? Similarly, you keep gas in a cylinder. Your cooking gas or whatever is kept in a cylinder. Now, how do you keep an extremely hot plasma? In what kind of a container can you keep an extremely hot plasma? For instance, if someone were to give you a plasma at solar temperature, 20 million Kelvin, that is the temperature of the solar interior. It's a hot gas, very hot plasma. So you can't keep that in a glass bottle or a metal container. It'll melt down, disintegrate completely. So you actually confine that hot gas, that hot charged gas, hot plasma, in what is known as a magnetic bottle. Magnetic field lines confine them within that field zone. So this process is known as magnetic bottling, and the technology that is developed is tokamak technology. The Russians developed it first because they were quite ahead in developing nuclear, I mean, not hydrogen bombs, fusion bomb. So it is in connection with that that they designed this technology. Here in Gandhinagar, there is a tokamak at the Institute for Plasma Research. If you're aware of the layout of Gandhinagar, I don't think you've come to the campus yet. If you're aware of the layout of Gandhinagar, as you go towards Ahmedabad from Gandhinagar, very close to Indira Bridge, there's the Amul Dairy office campus. Just next to it is the Institute for Plasma Research, where they have this technology. Anyway, that is just for general knowledge. So maybe one day you can go and visit this place. Your teacher over here, Professor Bhaskar Chaudhary, knows that place. He did his doctorate over there. So maybe you can ask him to take you on a visit to that campus one day, just to see these things. So here it is. So as you can see, these things have got real world relevance. Divergence of B is equal to 0. Incidentally, this divergence of B is equal to 0 has got also got a good deal of relevance in the phenomenon of the aurora, aurora borealis, aurora australis. If you have ever gone to the North Pole or the countries like Norway or Sweden or down south, countries like New Zealand, you will see aurora borealis and also it's a beautiful color display of light over the North Pole and the South Pole. So if you are very close to the pole, you will see such things over the horizon, above the horizon. So that is also related to this divergence of B is equal to 0 business. So as you can see, there's a lot of natural phenomenon connected with all these things. Anyway, so we have run out of time. In the next class, which is after your Deepavali vacation, that I think should be on the 10th. Today is the 29th. After this, you have next week will be Deepavali vacation for you. And then we are, as best as I'm aware of the timetable, we have a class on the 10th of November. So then we shall continue with this discussion on further topics, Ampere's law and all that. So I stop the sharing now. Somebody had questions. Let us look at those questions. I'll also stop the recording because the recording becomes a little heavy. But we can take up these